Greetings from Istanbul Technical University. I am Emre, the team leader of the İTÜ Rover team, and here we are, the fourth generation İTÜ Rover.
Based on the previous experiences from the last years, the fourth generation rover is designed for URC 2020. Optimal production of drive system, robotic arm, and science system were aimed.
This year's rovers utilize the rocker suspension design, which consists of rockers on both sides and a differential bar mechanism to facilitate the rover to overcome any obstacle. The rover is 1 meter in width and 1.1 meter in length. Rubber airless tires with aluminum rims provide superior grip and shock damping. To protect the motors, they are positioned inside the hubs. Thanks to the compact and lightweight space frame body design, it is easy to remove the electronics box or mount robotic arm and science system to the chassis.
The electronics core of the rover is suitable for both in-house and FRC robotic controllers. Smart motor drivers power the drive system and magnetic absolute encoders provide positions for closed-loop PID control. On the other hand, we are developing circuits for battery management, voltage regulation and sensory measurement for science system. Electronic components are assembled in a separate box to ease maintenance. Serial communication is used between the rover electronics and the ground station for controlling the drive system. For further communication, 2.4 GHz RF modules with 11 dBi high-gain omnidirectional antennas are used. LoRa RF modules, working at 900 MHz bands, are used for backup links.
We have been developing our new autonomous system using the robot operating system. The state machine model is used for simplifying the autonomous algorithm. A unique planner is created to reach the desired coordinates while avoiding obstacles. A new approach algorithm is activated upon arrival. A task-oriented camera system and OpenCV library are used to detect air tags in order to approach the gates. Thanks to the user-friendly interface, we can send the target coordinates on embedded maps and obtain the status of the rover.
The 6 degrees of freedom robotic arm uses a worm gear mechanism for each axis to provide the required torque and full rotation. All the axis casings, motor cases, and tubes are manufactured from aluminum. The two-finger end effector can sufficiently take the form of any object with the rubber material on its fingers. 7-brush DC motors are used to power the robotic arm and the end effector.
All rover's robotic arm system is equipped with the same motor drivers on the drive system, which gives the ability to obtain position data from encoders. With this input, the closed-loop PID algorithm is used for maintaining a smooth manipulation on all axes. Communication is managed through the CAN bus protocol. Thanks to its two-wire design, reliable and efficient cabling is possible.
We developed our inverse kinematics algorithm to perform difficult operations with great precision. This way, our end effector follows a smooth trajectory and provides great convenience to the operator. As a backup plan, forward kinematics is prepared against unexpected situations. Also, outdoor tests are accomplished along with the test in simulation environment. On the other hand, a model robotic arm imitating the pilot's movements is planned for simplify the arm control.
This year, İTÜ Rover Science Laboratory uses a vacuum system to collect samples. The system can take 3 different samples by using only suction force that is manipulated by a rack and pinion mechanism to collect samples separately and prevent contamination.
After sampling, to detect peptide bonds, Bradford reagent is used and the procedure is optimized for the rover to implement. Also, glucose molecules are analyzed with glucose biosensor that is designed and produced in our laboratories. In addition to these live detection methods, atmospheric gas sensors are used to support the results taken from İTÜ Science Laboratory.
The third sample will be examined by our custom Fourier transform infrared spectrometer. Discrete time Fourier transform is performed by the software to identify certain molecules. Furthermore, to analyze the rock samples, both on 532 nanometer Raman and near-infrared reflectance spectrometers that are developed by our science sub-team. Finally, the OpenCV library is used for crack detection of the ground to rock water.